Welcome, my dear students, this new session. In the last class, we discussed some property of a matrix associated with a linear map. In this class, we discuss about linear map associated with a matrix. In the previous class, we have a giving is a linear transformation from V to W, and then we have a basis. B and C is a basis. Then we can calculate the matrix related to the basis B and C. In this class, we discuss about we have any matrix is given, and then we have a basis, standard ordered basis also given. B and C are the basis is given. With the help of this basis and this associated matrix, we can find the linear transformation T from V to W, and that means we have any, if we have a 3 by 3 matrix, then we can say that R3 to R3 defined by some B is equal to some standard basis E1, E2, E3, and C is also is a standard basis. We have suppose F1, F2, F3, and we have any matrix is given. For example, we can say 1 0 2 0 1 3 1 2 and 1, and this is the matrix is given. Then because a 3 by 3 matrix is given, so any column of this is nothing but is equal to, you know that this is corresponding to the, so T of E1 is nothing but is equal to, can be written as a column vector 1 into F1 plus 0 into F2 plus 1 into F3 in this form. Similarly, we have a E2 is nothing but is equal corresponding the column vector in this basis. So this is 0 into F1 plus 1 into F2 plus 2 into F3 in the similar fashion. So with this we have to write a with the matrix we can write, because this matrix is nothing but is equal to, you know that the matrix, this is the form of a T of E1. First column is corresponding to the this basis C, and second is a T of E2 corresponding to the basis of a C, and this is equal to E1 corresponding to the basis of a C. This is corresponding to the E2, and then these vectors can be written as a finite linear combination of the element of the this basis C. So in this way we can construct a linear map associated with a given matrix. Okay, so that means let A be any matrix. We have a alpha ij m by n be given, and using this matrix A, we shall define a linear map S from U to V, where U and V are the vector spaces of a dimension n and m respectively. So we just say that into this form we can say that, so let B is equal to U1, U2, Un be a basis of we have a U, and C is V1, V2, Vn is a basis for V, be the ordered basis for U and V respectively. Then we define a linear map T from U to V by presiding values of S on the vectors of a B as follows. T of U1, we can just take T of U1 can be written as a alpha 1 1, means alpha 1 1 is a matrix, is you have a is a matrix in the form of this, you have a alpha 1 1, alpha 1 2 up to alpha 1 and in the similar fashion we can just say that. So this means we can say T of U1 can be written as alpha 1 1 into V1 plus alpha 2 1 is equal to V2. So like this we have a this is the matrix is alpha 1 1 alpha you have a this is alpha column is equal to, you have alpha 2 1, and then so on we get alpha of m1. So this is the first column corresponding to the T of U of the basis of a C. This means this can be written as a finite linear combination of the elements of the basis of a C. So alpha 1 1 into V plus this. Similarly, we can calculate the U2. So this is nothing but is equal to, you have a alpha of a 1 1 2 alpha 2 2 and so on alpha of m2. This is the corresponding to the basis for a T of U2 of the element of a base corresponding. So this is the element, any element of a U can be T of U2 can be written in the form of a this form. So T of U2 can be written in the form of a alpha of, you have a 1 2 V1 plus alpha of 2 2 V2 plus so on plus alpha of m2 Vm. And in the similar fashion we can write T of Uj, and T of Uj is nothing but is equal to alpha of 1j V1 and so on. And now we have to just say that in this case we just write into this, so we have to just, this is the jth column into this form, the corresponding this you have considered which is a coordinate vector is equal to 1j up to you have a mj, and then we can say that un is equal to this. So this means this can be, if you see this this whole thing can be written in the form of this form, and then we can say that extend this this is t, extend this t linearly to the whole of the u. The linear transformation t, this linear transformation to is unique. For this we have only note that the coordinate vector of a tuj relative to the basis c is the jth column of A. This means we can say that t of uj, this is nothing but is equal to coordinate vector of a corresponding to the c is the jth column is equal to you have a alpha 1j, alpha 2j, and so on. We have to just alpha mj is this. We have to take into this form. So the linear map T from U2 is defined is called as a linear map associated with the matrix A related to the basis C. So in the similar fashion we can just define a linear map. If we have any matrix is given and the ordered bases are given, with the help of this ordered basis we can write in the form of this thing. Okay, so we have it like this. We have a this is the matrix, for example, we have a giving. So we just say that you know that this is the column is nothing but is equal to you have a T of u1 corresponding to the C, and this is nothing but is equal to you have a this is equal to T of u2 corresponding to the column C. This is the scalars, and this is nothing but is equal to T of u3 corresponding to the basis sequence. So that's mean this means this is the element of this, and then you know that T from we have a here S. So in place of a T you can just put S. So S is equal to this, and then you can write as the basis of a respectively. So suppose we just take a S of this, we can write S of u1 can be written in the form of a 2 times of a v1. This can be written as a linear combination of these two vectors, and plus you have a v2 minus ka twice v3, and you have a plus ka v4. Similar fashion we can write S of u2 can be written in the form of a corresponding to this vector alpha 1, this is equal to minus 3 v1, and then we have a plus 0 into v2, plus you have a 1 into v3, plus 2 into you have a v4. And then last one we can write also S of u3 is can be written in the form of you have a 4 times of a v1, and then you have a minus ka v2, and then you have a 0 v3 is equal to 0 minus ka 2 times of a v4. Now S of u1, S of u2 and u2, if we have any arbitrary vector u can be written as a linear combination of a alpha 1, alpha 2 and so on. So we just say that if we have a u is any arbitrary vector set to v3, then can we say that u can be written in the form of a linear combination of this alpha 1 u1, alpha 2 u2, alpha 3 u3, and then if we have to calculate the t of u, alpha 1 t of u1 plus alpha 2 t of u2 plus alpha 3 t of u3. That means this can be written in the form of this, or we have a S, so we have to operate the S here. So this is S, S and S. Substitute the value for u of S1, u of S2 and u of S3, and then here have know the value for this scalars. That means we can construct a linear transformation in this way. Okay, so we are I just tried already. This can be written into this form. So this linear extension can extension of this definition of S as the basis of the required map of S. Okay, so now if we have in place of the same question I take this one, we have to define into this form. So we have if we take a S of u1 means you have a standard basis. So if e1 is equal to you have a f1 plus 2, this is nothing. We have a b is equal to you have a e1, e2, e3, and c is equal to you have a f1, f2, f3, f4. These are the standard basis. So if these are the standard basis, then we can see clearly S of you can calculate e1 is equal to e1 is equal to you have a e1 is equal to you have in the form of a 2 times of a v. So 2 times of a f1 plus you have a f2 minus ka 2 times of a f3 and plus you have a f4 4. If you simplify this can be written in the form of a you have a 2. This is can be written in the form of a like this. This is a linear combination of a this can be written in the form of 2 of 1 0 0 0 plus 0 1 0 0 plus you have a minus sign, so minus you have a 2 times of a 0 0 1 0 and plus 0 0 0 1, and this can be written as a you have a 2 times you have a 1 minus 2 and 1. So S of E1 is equal to this form. Similar fashion we calculate S of E2. So S of E2 is equal to, I just take it this form, you have a, because of the standard basis we have a minus 3 and 0 and you have a 1 and you have a 2, and similar fashion we can calculate S3. S3 you have a 4 minus 1 0 and minus 2. So this means we calculate all these vectors. Now we take a any arbitrary vector. Suppose you have a x y z belongs to the you have a v3 or r3 whatever this. So this means x y z corresponding to a standard basis can be written as x of e1, y of e2 and z of e3, and then t of x y z can be written in the form of a x times t of e1 plus y times t of sorry is s, so s we can operate s, so this is s e1 s e2 plus s e3. Now we just take the value for substituting the value for this. So we have a s of x y z is equal to x times we have a s of e1 is equal to you have a this, so you have a 2 1 minus 2 1 plus y times you have a s of e2 is equal to you have a 4 minus 1 0 minus 2 plus z times you have a e3 is equal to you have a, sorry, this is e2 is wrong, is e2 is equal to you have a minus 3 0 1 2 and z is equal to e3 is equal to 4 minus 1 0 minus 2, and then this can be written as you have a 2x minus 3y plus 4z, and then you have a x, second term is a x, and then you have a minus z. Now you have a minus 2x plus y, and then last one is you have a x plus 2y minus 2z. So this is the general transformation x y z we calculate into a this form. So this is the for corresponding to the standard basis. So like this we have to take this form. Okay, I just take it in this form, I write in this form of this. So this means we can take into the form of this thing by this matrix, and now you just say that I just take it into this form. This is the general linear transformation we have to construct it for the given problem. Okay, let's try this one more problem. Here I just take a represent a basis, standard basis B, because we have a v3 to the v3. So this means we can represent it into this form. So we can calculate t of e1 0 1 first, t of 1 0 0, and this can be written as a 1 into 1 0 0 plus 2 into 0 1 0 plus 0 into 0 0 1, because B and C bases are the same. B and C are the both are the same basis. So this can be written in the form of we have a this is equal to 1, this is equal to 2, and then we have a 1 2 0, and then we can say t of 0 1 0. This can be written as a minus 1 times you have a 1 0 0 and plus 3 times of a 0 1 0 and plus 0 times you have a 0 0 1. This can be written as a you have a 1 and you have a 3 and 0, and again you have to calculate the value for 0 0 1. This is can be written as a 0 times you have a 1 0 0 plus minus 4 times of a 0 1 0 and plus 1 times is a 0 0 1. This can be written as a first term is equal to 0, then you have a minus 4, and then you have a 1. So t of e1 e2 e3 we have to calculating. Now we have to just write x1 x2 x3. So t of e1 e2 e3 I already calculated. Substitute here this is here calculating this form. Now we have to substitute the value for all these things equal to T of E1, T of E2, T of E3, and then we can just say that this can be written in the x times T of E1 is equal to, you have a 1, 2, 0 plus this is x2, this should be x2, x2 times T of E2 is equal to, you have a minus 1, 3, 0 plus x3 is equal to, you have a 0, minus 4 and 1. Then we can say that simplify this is equal to, you have x1 minus x2, this is 0, then you have a second term is a 2x1 plus 3x2 minus 4x3, third time first term is equal to 0, second term is equal to 0, then you have only for x3. So this means we can say that T of x1, x2, x3 is general linear transformation. If you substitute the value this, so we just say that into this form. Okay, so this means we can take into this form. So this is clearly a general form of this linear transformation. We getting into this form. Okay, so now I take this. We have to just say that this is matrix, very simple. I take this identity matrix, and then we take also the basis is identity. So this means we have to get the identity transformation by the of this. So we have to take a T of 1 comma 0 is equal to, you have a, this is a 1 comma 0 comma 1 plus 0 times you have a 1 comma 0. This can be written as a, you have a 0 1, and now T of, you have a 0 1 can be written as a 0 into 0 comma 1 plus 1 into 1 comma 0 is equal to 1 comma 0. So if we have to find the T of x1 x2, so T of x1 x2 can be written as a some x1 T of 1 comma 0 plus x2 T of 0 comma 1 sorry T of T of 0 comma 1, T of 1 comma 0, and then we have a x1, and then T of this is, you have a 0 comma sorry, this is the first sorry this is correct, okay, sorry, this is x1 T of 1 comma 0 plus x2 T of 0 comma 1, x1 T of 1 comma 0 is equal to your 0 comma 1, x2 you have a 1 comma 0, then you have a clearly you have a x2 comma x1. So because if we take change the order of a basis, so this means you have a, if we getting the identity matrix, but the order should be the change. I already explained you this into the previous classes. That means we have a identity transformation, then this matrix is always is the identity matrix, but it depends upon the identity columns of a this can be changed accordingly to the order of the basis of this thing. Okay, so now I just say suppose we can I just prove this is equal to this form, so we have a like this way. Okay, now we have to get this. I take some different basis, and we have to again from R3 to R2. So I just calculate first is equal to T of 1 1 0, sorry 1 1 1, I'm sorry 1. This can be written as a coordinate vector of this is equal to this 1 comma 1 plus you have a 3 times 1 comma minus 1. This is equal to, you have a 3 plus 1 is equal to 4, and you have a minus 2. Then we calculate T of 1 2 3. This can be written as a minus 1 1, and you have a 1, and plus you have a 1 into 1 comma minus 1. Then you have a, this is equal to minus 1 or minus 1 or plus 1 is equal to, you have a clearly this is equal to 0, and this is a minus 1 is equal to minus 2, and then now we have a T of 1 0 0. This can be written in the form of a 2 times of a 1 comma 1 plus 0 comma 1 comma minus 1. This is nothing but is equal to, we have a 2 comma 2. Okay, so this means we have to calculating. Now we have to take any x y z is the element of a R3, then this x y z can be written as a finite linear combination of the elements of a this thing. So this is this IO. Okay, just means x y z can be written in this form. Now we have to find the value for alpha beta gamma in the terms of x y z. So this can be written in the alpha plus beta plus gamma, and you have a alpha plus you have a 2 beta, and you have alpha plus you have a 3 beta. So we can simply say that x alpha plus beta plus gamma is equal to we have a x. Now alpha plus we have a twice beta is equal to you have a y. Now alpha plus you have a 3 beta is equal to you have a z. If we have to subtracting these two equations, so we getting clearly minus beta is equal to you have a y minus z. So beta is equal to you have a z minus y. So beta is equal to you have a z minus y. Then substitute the value for beta. We can say that alpha is equal to you have a y minus twice beta, and then you have a y minus twice z plus 2y. Then किसके relative y minus का 3y minus 2z. Alpha is equal to this. So gamma can be written in the form of x minus alpha minus beta. So x is x as it is. Alpha is equal to you have a minus ka 3y plus ka 2z, and beta is equal to you have a minus ka z and plus ka y. So this can be written as a x, and then you have a minus ka 2y, and then you have a plus ka z. So this is a gamma. So this means this equation x y z can be written in the form of a alpha. Alpha is you have a 3y minus ka 2z, and then you have a 1 1 1 plus you have a beta is you have a z minus y, and then we have a clearly you have a 1 2 3, and then plus you have a x minus 2y plus z, and this is nothing but is equal to 1 0 0. Okay, so now our objective here to find the general linear transformation. So we substitute the value for here t, and then we have to calculate this thing. Okay, this we have to simplify this. I already explained you. This is we have to this is okay, this is a mistake here. So this is here is a beta is equal to z minus y. So this is beta is equal to z minus y. So this means solving this equation we find into this form. Now we can I already explained you this can be written into this form, and now this is e1 is equal to you have a 3y minus twice z, and t of e1 e2 e3 we have to calculating 4 minus 2, and then you have a this value is equal to 4 minus 2 plus you have a z minus y, you have a I think 0 comma minus 2, and plus you have a x minus 2y plus z, you have a 2 comma 2. So now you have a this is equal to 4 3 is a 12y minus ka 4 2 is a 8z, and then you have a this is term is 0, so you have a plus 2x plus ka minus ka 4y and plus ka 2z, and then next term is equal to minus ka 6y plus ka 4z, and then you have a minus ka 2z plus ka 2y, then we have a plus ka 2x minus ka 4y plus ka 2z. Now this is can be written in the form of a twice x, and this is equal to plus ka 8y, and then you have a minus ka 6z, and next term is equal to you have again 2x is here, no x term is there, so you have a twice x. Now you have a minus 6y, and then you have minus 4y, then you have a minus ka 8y, minus 6y minus 4y minus 10y minus plus ka 2y, then this is equal to, then you have a this is equal to plus ka 4z, and because it's a 4z minus 2z plus 2z is equal to this. So this means t of x y z can be written in the form. So this is the general linear transformation we have to calculating into this form. So okay, just take into this form, we just take a 2x plus 8y minus 6z, 2x plus minus 8y plus 4 as z. This is the general linear transformation. This can be verified that if you have a took a t of 1 1 1, then you just take is equal to 2 plus 8 minus 6, 2 minus 8 plus 4, and then you have an clearly is equal to, you have a 0 comma minus ka 2, and then you have a, if you have a 1 2 3, then you can say that 1 is equal to 2 and a plus 16 minus ka 18, and then you have a 2 minus ka 16 and plus ka 12, and this is nothing but is equal to 6 to 18 is equal to 0. 12 plus 2 14 is equal to minus 2. So this is sorry, this is just a minute. This is this is equal to 4. This is 4 and minus 2. This is 4 minus 2, this is 0 minus 2, and then if you have to take a t of 1 0 0, this is nothing but is equal to, you have a 2, and then you have a clearly you can say that this value is nothing but is equal to 2 2 2. So this verify all this thing into a this case. So I just move to the one more result here for the end of this part. We just say that V and W be a finite dimensional vector spaces. N and M are respectively. B and C are the ordered basis for V and W respectively. Then we can say that this L of V and W is isomorphic to Mn, where Mn denotes the vector space of all M by N matrices. So this means we can generalize this into this form. So just we take a starting the proof. Consider the map pi from LV to Mn, because we have to show that these two maps. So this means we have some map from L of VW to M cross N, which is 1 1 and onto, and also linear. So if we take a pi as any map, which is well defined, linear, and if we have a show that this is a 1 1 and onto, then this clearly these two maps are isomorphic to each other. Okay, so we start from this pi is this defined into this form, and we have to take a pi is nothing but is equal to, we take a pi of t is any linear transformation. This t is the element of a, you have a L of VW, because L of VW is nothing but is equal to collection of all the linear transformation from V to W. So this is the we have a matrix corresponding to the basis B and C. So where B is equal to V1 V2 Vn, dimension of this is equal to n. So this is basis. C is equal to dimension of M. So we have a W1 W2 Wm is the basis for we have another linear map basis, the ordered basis of a V and W respectively. Now clearly phi is well defined. You take a pi of t is equal to pi of s, then t matrices are the same. If matrices are the same, the corresponding columns bases are the same. This is well defined. Okay, so now we have to take any t is equal to s, then pi of t is equal to pi of s. So we have to just take a, first show that this pi is a linear. So let alpha and st and be this thing. So this means we can say that pi of s plus t, this can be written by the definition of this. Now by we already proved that this is the same as a this can be written in the form of s of bc plus we have a t of bc, and this is nothing but is equal to, you have a pi of s plus pi of you have a t. So this is clearly satisfied. Now we have a, again pi of, you have a alpha of s. This can be written in the form of a, clearly you have a span of alpha of s is equal to b of t, and by the I already proved this result also. This can be written alpha times of a s b of c, alpha time of a, you have a pi of s. So this means this pi satisfy both the conditions of a linearity, additiveness, and the homogeneity. So this means we can say that clearly this pi is defined, well defined, and also is a linear. So we just say that this is also is a linear. Okay, so that means pi is a linear. Now we have to show that this we define a, so we show that pi is a 1 1. If we show that pi is 1 1, that means we have to s is equal to some beta ij, and t of c is equal to some coordinate vectors corresponding to the basis is equal to this is equal to, you have a alpha of ij. So this means we can say that pi of s is equal to pi of t, then this is equal to this. This means we can say that clearly alpha ij is the same as a beta j, and this means these two matrices are then the corresponding elements are the same. So this means beta ij is equal to this. So we are starting from this s and t. and then we can show that these two are equal, and this is nothing but is equal to, we can say that this means is 1 1. Now we can say operate the S of Vj is nothing but is equal to, right, the alpha beta ij wj, and this means w beta ij is the same as a alpha ij, so this can be written as I running 1 to an alpha ij w, and this is nothing but is equal to same as a v of t of vj. So means for all j, S of Vj is equal to t of Vj. For this means phi, so v equals pi of S, then we can say that S of t, S and t are both the equal. So this implies that we can say that for all t, this S and t are the same. So we're starting from pi S is equal to pi t, and then we have to show that this two S and t are the same. So this clearly this pi is a 1 1. Now rest we show that the onto. For onto we have this because pi from vw to mn is a defined into this form. For every t we see belongs to, this is the belongs to the m. For every t alpha ij is belongs to the m, then there exists a linear transformation. We have to just say that if this belongs to m, then there exists a linear transformation t from this map. We already know that this previous. Then we can say that pi of t is equal to this thing. So this means clearly we show that this is also is a onto. So hence pi is a onto, since pi is a linear 1 1 and onto and a isomorphism, and then this is equal to, we can say that L of v and w is isomorphic to any matrix m by n, and vb1, and then we can say that also by the definition of L dimension of this is because of the matrix is equal to this, then is all the m by n is columns are linearly independent. So that means is a form a basis of this columns base span and form a basis. So this means we can say that this is a dimension of this clearly is a mn is there. Okay, so now I just complete the proof of this in this form up to this. So this means I just this all this about this associated matrix and matrix associated linear transformation, and linear transformation associated the matrix representation. Okay, so I stop today's lecture here, and in the next class I will continue about the how to find a rank, nullity, rank and kernel of a given matrix. So we discuss in the next class is the rank, nullity, dimension, dimension of a range and dimension of a null space of a matrix in this class. So thank you very much for this.